Hello everyone, I'm high school physicist and welcome back to my channel. This is my 7th video. My motivation in creating this channel is to talk about some topics in physics for an audience at high school level or above. Today I'm going to be talking about a topic entitled Perihelion Shift of Planets. The agenda for today is the question formulation, the answer, a mathematics enrichment, and conclusion. Before starting, let me mention the maths needed to follow my story in this video, which includes ellipses, trigonometry, which are sine and cosine, graphs, and calculus differential with differential equations. This calculus is for the enrichment part only and can be safely skipped. The question is simple. You are asked, can you present perihelion shift of planets mathematically? Yes, the logical steps to follow this problem would be to know what perihelion is, to know what perihelion shift is, and finally, can we find a mathematical form to describe it? In solving this problem, I will use a two-dimensional flat space for simplicity. Firstly, Kepler's law says that a planet's trajectory is elliptical with the Sun at one of its focus. Let us see this hypothetical planet trajectory. Let x and y be in millions of kilometers. Let us also assume that the period of this planet is 1 year. Sun is at the coordinate of -8, 0, which is at one of the focus of the ellipse. Perihelion is a point where the planet is at the nearest distance to the Sun, while aphelion is a point where the planet is at farthest distance from the Sun. Now let us talk about perihelion shift. The trajectory of planet that undergoes perihelion shift is shown in the illustration on the screen. The planet moves in counterclockwise manner. There is a slight shift on its path from year to year. Black is the first year, red is the second year, and blue is the third year. Let us now zoom into the second quadrant of this planet's trajectory, because this is where the perihelions reside. Please be aware that for other cases, the perihelions can reside in any quadrant. I drew a purple dashed circle to guide me in locating the perihelion. And these are the perihelions from year to year. And our task is to measure or calculate the perihelion shift angle, which is phi. Phi is measured in degrees per year, and in reality the shift is very small, which makes the unit of arc seconds per century is more appropriate. After knowing what perihelion and perihelion shifts are, let us now see the elliptical shape. In Cartesian coordinate, this ellipse can be written in mathematical equation as x squared over 100 plus y squared over 36 equals 1. And then we move the left focus of -8, 0 to the origin of the new graph on the right by translating this ellipse 8 units to the right, and the new elliptical equation is shown as on the screen. In this case, it is easier for us to work with polar coordinates. As a note, understanding coordinate systems such as Cartesian, polar, spherical, or cylindrical is essential in physics. Subsequently, we have to convert xy into r theta with some conversion formulas. A equals 10, b equals square root of 36, and e, or ellipse eccentricity, is equal to 0.8. Hence, The equation of this ellipse in polar coordinate is r equals to 18 over 5 minus 4 cosine theta. Having found the equation of the ellipse in polar coordinate, mathematically, the perihelion shift is obtained by modifying theta with rho theta, with rho being a constant or a number. Physicists will feel that the new factor rho must be a number close to 1. Here I plotted r as a function of theta for two cases, which rho equals 1 at left blue plot and rho equals 1.5 at right plot. Vertical axis shows the distance of the planet from its star, and the horizontal axis shows the theta in radians. One wavelength is 1 year. We are now ready to calculate the amount of perihelion shift or aphelion shift, the same, by comparing cosine theta and cosine rho theta. We superimpose the two plots from the previous slide. A note, I have shifted the red curve to get the correct zero reference. The perihelion shift is thus 3 pi minus 7 over 3 pi, which is 120 degrees per year. Hence, the perihelion advances by 120 degrees per year. We now arrive at the enrichment part. You may skip this if it is too technical for you, but believe me, it's worth watching. We start with the result from non-relativistic classical physics, in which there is no perihelion shift or rho equals 1. Let us define u as reciprocal of r. With this, differentiation will be much easier. Let us now differentiate u with respect to theta, and then we differentiate again. Then we obtain d2u over d theta squared plus u is 5/18. In general, we can write d2u over d theta squared plus u equals k, with k is a constant, and for our case, k is 5/18. Let me rewrite the general result from the previous slide, and this is the best part. More accurate theories, which are special relativity and ultimately general relativity, provide correction to this equation. Using these relativity machineries, we can add terms as a function of u at the right-hand side of the equation, a kind of series expansion. K1, K2, and K3 being constants. As usually, physicists like doing these kinds of things. And to get our result, we have to substitute K1 and K2 as follows. And dear viewers, please verify this yourself. It's a good thing to practice. In conclusions, we have learned about perihelion shift of planets. This phenomena can be explained mathematically using ellipse in polar coordinate with modified parameter, that is theta into rho theta. We have calculated the amount of perihelion shift in degrees per year. And finally, I have shown you the contribution of more accurate theory, that is relativity, to explain the origin of rho factor. In this occasion, I want to thank my proofreader Dark Calligraph. If you enjoyed watching this video, please support the High School Physicist channel via a subscription and like. Thanks for watching, and I'll see you next time.